Good morning, everyone. My name is Ubongabasi, Inyang. I'm from the Manchester Metropolitan University, and I'll be presenting our paper this morning on Interoperability Imperative, a built environment maturity barrier analysis for data twin convergence with BIM and IoT. I'll take you through our motivation and methodology, our barrier taxonomy, the core maturity barrier logic model across 5 levels, our diagnostic implementation guideline, stakeholders implications, and then the conclusion. The industry is undergoing a shift from static to dynamic data-driven asset representation enabled by the convergence of BIM, IoT, and digital twin technologies. I'll first start by defining digital twin as a virtual representation of a physical asset that is continuously updated through automated bidirectional data exchange, enabling real-time monitoring, prediction, and optimization. Now, despite these promises, most deployments stall, and that is what we call the interoperability imperative. The need for heterogeneous systems to not just exchange data, but to be able to understand and interpret data without any ambiguity. To be able to answer this question, we carried out a Prisma-guided literature synthesis where we identified 1,089 records and we distilled about 180 studies. From this corpus, we identified 2 predominant research streams. We also extracted barrier taxonomy and the maturity barrier logic that maps specific barrier to specific transition stages and created a diagnostic tool. The barrier taxonomy has 2 broad families. One on the technical side, from semantic interoperability, where systems can't interpret each other data through data integration challenges, connectivity, and latency issues to data quality problems. On the organizational side, we see skills gap, resistance to change, structural fragmentation, departmental silos, high capex, unrealistic and unclear ROIs, and crucially, trust and security concern over data ownership and AI decision making. The key insight here is that specific constraints impasse each digital maturity barrier, and that's what brings about the maturity barrier logic model. So going through the journey, the first one is level 1, which is the digital model. That is a high fidelity BIM model. Now the barrier here is that of digitalization gap. Legacy drawings, fragmented CAD, and high cost of scanning is hindering organizations from creating a trusted machine-readable baseline. We can learn from the empirical case study from the Northumbria University, where they were able to adopt the ISO 19650 BIM standard to establish a standardized digital foundation that enables all subsequent digital twin maturity. So the key takeaway here is that digital standardization is a prerequisite for digital twin maturity. When we move from level 1 to level 2, now level 2 is a real-time one-way data flow from physical asset to digital asset models. And the key barrier here is that of connectivity. And this happens because legacy building management system uses incompatible protocol, and the BIM and the IoT are disconnected, and hence data flow is manual or asynchronous, and the virtual model never really reflects the actual operational reality. There are 2 case studies that shows how to resolve this. One is from the University of Florence, where they were able to map the IoT using the middleware Node-RED. And we also have the University of Florida case where they use custom IFC property sets to be able to link dynamic sensor data to the BIM object. Now, the key takeaway here is that middleware and interoperable data integration are non-negotiable for real-time monitoring. Level 3 is the adaptive twin. This is the most critical transition in the entire model, where AI uses historical data to predict future states. And the barrier here is that of semantic gap. Even when connectivity exists, data are flowing. The system still cannot contextualize what that data means. Let's say, for example, the sensor in this room reads 25 degrees. The system might know it's 25 degrees, but does it know that pump A fits into this room, or that pump A fits into the north wing of this hotel? There is data flow, but no machine understanding. And we can learn from the Institute of Manufacturing case, where they resolve this by mapping their IFC data to the brick schema ontology using RDF and OW. So, and creating a knowledge graph that enables fault detection and diagnosis automatically. So the key takeaway in this is that ontology-based integration is what transforms a digital shadow into a predictive twin. We go to the level 4. Level 4 is the cognitive twin, an autonomous decision-making, self-learning, and where actually a digital twin can actuate the building. The barrier here is no longer technical, it is trust. The black box AI, unclear data ownership, cybersecurity risk, and primary privacy concerns. This means that stakeholders refuse to grant autonomous actuation rights. Technical capability exists, but human confidence does not. Now, we've seen this through literature that this is the predominant barrier to autonomous digital twin deployment. Organizations will not allow AI to control their physical assets without transparent governance, regulatory compliance, and trusted decision-making framework. So the key takeaway here is that technical capability alone is insufficient. The socio-technical dimension is determining. And then we go to our level 5, the federated digital twin, a system of systems where multiple digital twins across organizations, buildings, cities interact and optimize together. The barrier here is that of standardization. Independent digital twin uses different data standards, have no trusted exchange mechanism, no shared governance, so they remain in silos. We can learn from the Smart Dublin Urban Digital Twin project, where they were able to align the multi-owner collaboration using the EU Data Governance Act to establish a formal trusted data space. So the key takeaway here is that a federated twin is not a ledger digital twin. It is a trusted ecosystem built on common standards and shared governance. This slide presents our diagnostic implementation guide for resolving semantic guidelines and transitioning from digital shadow to an adaptive and cognitive twin. This guide works in 3 steps to address 3 failure modes that co-occur in stalled systems by showing how to contextualize data with ontology mapping, enable semantic querying with Spark QL, and abstract raw sensors streamed through semantic middleware. The outcome is machine understanding, not just data flow. This presents specific responsibilities across 3 groups. So asset owners must transition from being passive to becoming active drivers of digital continuity by embedding interoperability and semantic data requirements directly into procurement contracts. Technology providers must abandon closed proprietary architectures and adopt open modular systems, while policymakers must establish regulatory frameworks aligning with the likes of EU data governance and promote smart readiness indicators as benchmark for building digital twin readiness. To conclude, digital twin maturity is not a linear technological evolution. It is a sequence of constrained transitions, each blocked by a specific interoperability barrier. Most implementations stall at level 2, the digital shadow. System achieves synthetic connectivity but lack ontology-based interoperability for machine understanding. The future of digital twins depends not on more sensors, but on a semantic interoperability and trusted governance ecosystem. And a federated digital twin is not a bigger digital twin. It's a trusted ecosystem where independent twins collaborate through shared standard and governance. Our framework provides both the analytical model and the practical diagnostic tool. Future work should focus on empirical validation, quantitative ROI assessment, and automated ontology mapping techniques. Thank you.